for the start, for the introduction. Wonderful. Welcome, everyone. Thank you for waiting. We were arranging all the technical details. And then today we are with you for the last session with the true content, namely post-quantum cryptography and Shor's algorithm. Today we have with us Dustin Moody from NIST, the National Institute of Standards and Technology. He is one of the first mathematicians in our program to present here. Thank you, Raj, for arranging. And Lizzie, great. He is one of the first mathematicians to present here. He obtained his PhD from the University of Washington, and now he is at NIST leading the post-quantum cryptography project. Very important to make our future quantum resistant. Very happy to have you here, Dustin. We look forward to hearing everything about it. I will share your slides. Questions will be posted on Discord that we will keep an eye on. And after your presentation, we will field the questions from participants to you. Please take it away, and thank you very much in advance.
Thank you very much for the invitation to talk. Sorry, technical difficulties always seem to slow things down, and glad to be here. So today I will talk about the NIST post-quantum cryptography standardization project and what all that is about. So yeah, go ahead and go to the next slide. So I'm sure you're probably quite familiar with quantum computers. This is a very fascinating technology that has been gaining momentum, and a lot of progress is being made. Of course, these computers will be able to do a lot of very important and impressive things. It will increase our computational power to do certain applications and problems, but they won't be able to do absolutely everything. They are not universal machines, and there are some limitations, which are challenges that engineers and people working on them are trying to overcome. So go ahead to the next slide. Now, I'm in the field of cryptography, and we'll see that there are some effects that quantum computers will have on cryptography. And quantum computers have been, of course, around for a couple of decades of people working on them. And it seems in the past 5 years or so, we're seeing more and more headlines in the media and in news dealing with progress being made by various companies and organizations and academic groups who are building larger and larger quantum computers. So let's go to the next slide. So it turns out that besides all the positive applications, there are two algorithms that are known that give cryptographers a little bit of a headache that we have to be concerned about. The first was discovered in 1994 by Peter Shor, and it was a quantum algorithm that gives an exponential speed up over classical computers that could do two different things. The first thing is that it could factor large integers. So it's very easy in your head, if I tell you what prime numbers multiply to give you 35, to say that it's 5 times 7. On the other hand, if I give you a number that is hundreds of digits long and ask you to factor it into its prime factors, it turns out that that is very hard for computers to do if you choose the numbers big enough. And there's another mathematical problem that Shor's algorithm also turns out to solve. It's pretty amazing that it solves both of these. It's called the discrete logarithm problem. And I won't give you the technical kind of definition of that, but it involves finding the order of an element in a generic group if you've had abstract algebra. So Shor's algorithm was discovered in 1994, and like I said, it could solve those two problems very, very efficiently. You could solve them in polynomial time if you had a large enough quantum computer. A couple years later, there was another algorithm discovered by Love Grover that could give a speed up in a more generic circumstance. If you're just, say you have a table and you're wanting to search through that table and find one particular entry that satisfies your requirements, kind of an unstructured search, it gives you a polynomial speedup from, say, if your table has n elements, naively that would take O of n time to search through. But with Grover's algorithm on a quantum computer, you could do it in O of square root n time. Okay, so let's go to the next slide to see the impact of these two algorithms on cryptography. So NIST has various cryptographic systems that we have standardized, and they get widely used around the world to protect our information. Crypto systems can be broken down into a couple different kind of buckets or families. There's what's called public key cryptography, and there's what's called symmetric key cryptography. Symmetric key cryptography is when you and your user, you and the other partner share the same key, and you can encrypt and decrypt information back and forth using that same key. And that gets widely used. An algorithm called AES is a block cipher that is typically used. But there's also another part called public key cryptography that you need to use in order to create that shared key with your partner. So for public key cryptography, we have algorithms like RSA, Diffie-Hellman, elliptic curve Diffie-Hellman, as well as digital signatures. When you want to electronically sign a document and have someone be able to authenticate that you created that signature, that also uses public key cryptography. So it turns out that Shor's algorithm would break all of the widely used public key crypto systems that we implement today. RSA, Diffie-Hellman, elliptic curve cryptography. Shor's algorithm breaks them all once your quantum computer gets large enough. So of course that's very worrying to cryptographers because we want to be able to protect your data. I also mentioned Grover's algorithm. Grover's algorithm would have an impact on the symmetric key algorithms, but the impact is not as dramatic because Shor's algorithm gave you an exponential speedup. Shor's algorithm is only a polynomial speedup, so it won't completely break the symmetric key algorithms like AES. It means we will need to use longer key sizes, but that's more manageable. We don't have to completely change out the crypto system that you are using. So this is the threat that quantum computers pose to cryptography. And because NIST has standardized some of these crypto systems, and this is industry and governments around the world use these crypto systems, it was we knew that we needed to do something to replace the crypto systems that would be broken. So let's go to the next slide. Big question then is, well, how soon do we need to worry about this? If quantum computers don't come around for 100 years, this won't be my problem. This will be somebody else's problem. So next slide. To help us understand, though, it turns out you can actually have a problem. You can be at risk even though a quantum computer has not yet been built. And this is a little informal theorem due to Dr. Michele Mosca that helps you understand this threat. So it involves three variables, x, y, and z. X is how long you need to protect your information. And that will vary depending who you are. If you're protecting national security, X will be a very big number, 30 years, something like that. If you're an organization protecting medical information or financial information, various regulations will tell you what X needs to be. Y is the variable of how long it's going to take us to standardize replacement algorithms and get them adopted around the world. And from experience, NIST has worked with cryptographic transitions. Y is never as quick as we would like. Y is typically going to be 10 years, 15 years to transition to new cryptographic algorithms. And Z is the time until you have a quantum computer that's big enough to break cryptography. So with those three variables, what this theorem says is if X plus Y is greater than Z, you actually have a problem today, even if a quantum computer has not yet been built. And that's because of this threat that's often called harvest now, decrypt later. Your enemy or your adversary could copy down your data. Even if it's encrypted, they could just copy it and hold on to it. And they can't read it because it's encrypted, but they can just hold on to it and wait Z years until the quantum computer comes along and they'll be able to get access to it. And if Z is less than X plus Y, you will not be providing the X years of protection that you would hope to, because you first need to wait the Y years until we have new crypto systems ready, and they'll get access to your data. So I already told you what kind of some numbers for X could be and what Y could be. And then a question will be, well, what is Z? Let's go ahead and go to the next slide. Wanted to show, like, this is an example of the White House taking this very seriously. Back in May, they issued a national security memo telling the federal government and federal agencies that NIST is working on this, and you all need to be aware of this and be ready to transition quickly to the algorithms that will be selected by NIST. So let's go to the next slide. In looking at what Z will be, Dr. Michele-Mosca and some of his colleagues have done various surveys of experts in the field to find out when they think a quantum computer will be built that is big enough to break RSA 2048 in 24 hours. So that would be breaking a modern crypto system in one day. Now, these are estimates from experts. Nobody, of course, knows when a quantum computer will be built. We can't predict that with certainty. History report has a lot more information in it, but this is the main chart that summarizes the findings from this survey. So if you look at the rows in this chart, the bottom row there says 5 years. And if you look at the color-coded options, you can see that most of the experts that were surveyed think it's a pretty small chance that we will have a big enough quantum computer in 5 years. If we go out to 10 years, they start giving a little bit more on their percentages. And if you get up to 15 years, you see that well over half, well, about half of the people they surveyed think we could have a quantum computer in 15 years. So that gives us maybe some kind of idea for what Z might be. Maybe 10 years, maybe 15 years, maybe 20 years. That's kind of the time scale that we need to work with as we think about this threat from quantum computers. So next slide. So what is NIST? Before I say what NIST is doing about this, when you hear the words quantum in cryptography, there's another kind of topic that comes up that I want to make clear what it is and how what it's different from the project NIST has going with post-quantum cryptography. So quantum cryptography is the idea of using quantum technologies to build crypto systems. And that's different than the threat I talked about where a quantum computer would break the crypto systems we use today. So there are people working on this problem as well. There are companies that are selling products to build crypto systems using quantum technologies. And the very interesting thing is, theoretically, you can do this so that they are guaranteed by the laws of physics. You will have unconditional security. And that's not something we can do with classical computers today. So that's very cool. Now, there are some limitations. This is, in theory, you can do this. In practice, we're still working on building the tools and everything you need to make that happen in practice with enough, removing enough of the errors so that you get those guarantees. You can do encryption, but not authentication. It turns out this is not very scalable. It's hard to make this work over very long distances, and it needs expensive and special hardware. So there will be applications where this is useful, especially very high security needs. For example, China has built a quantum network to do this kind of thing. They've even built a satellite that exchanges information using quantum cryptography. But this is not the focus of the NIST post-quantum cryptography project, because this will be used in certain applications, but it's not going to be deployed on the internet and on our phones and what's to protect most of our information around the world. Okay, so next slide. So NIST started a project back in 2010 to help the world get ready for the quantum threat to cryptography. And this is generally kind of called post-quantum cryptography or quantum-resistant cryptography, where we were looking for new crypto systems that would be protected against attacks from quantum computers. For the first 5 years, we were building our team and just kind of getting our understanding. And around 2016, we started taking some concrete steps to create the first standards. So basically what we did is we launched a large-scale international competition where teams from around the world would design crypto systems that they believe were protected from attack from a quantum computer and send them in to us. And we would manage a process of evaluating which ones were the best, along with the external cryptographic community. And at the very end of the process, we'd have the algorithms, and we would standardize those algorithms for people to begin using. So this timeline kind of shows we went through a series of rounds. We initially had 82 that were sent in to us. And where we are now is we just concluded a third round of evaluation. And at the end of the third round, we selected a few algorithms that would be the ones people will ultimately begin using to provide protection. So I'll give you a little bit more information on this. This is our NIST post-quantum crypto team. We have a variety of experts with different backgrounds. And nonetheless, it's not a huge team. It's around 15 people at a time who are actively working on the project. Let's go to the next slide. So you might wonder how we select a crypto system to protect us against quantum computers when we don't even have quantum computers. Here's the criteria that we were focused on. Number one, it needed to be secure against both classical attacks and attacks from future quantum computers. Number two was performance. We would measure this on various classical platforms, both high-end servers and more lightweight devices, to see how efficient these crypto systems were. Obviously, if something's too slow, we won't be able to use it. And then we had a number of other criteria that were important that we hoped the various crypto systems would satisfy as much of these things as possible. I don't think I need to go into details on those, though. Security and performance were the main two criteria. So let's go to the next slide. In terms of security, we defined 5 security levels. And even this was a challenging task because there's no consensus way as to measure security against a quantum computer that hasn't yet been built. But we needed a way so that when submitters sent in a crypto system and provided us with concrete parameters, that they could give us an estimate of how much security they were providing. So we defined 5 security levels that related back to the security of crypto systems that we already have standardized. And then we described how you could measure security in a variety of metrics to try and estimate, how many gates would be required, both classically, quantumly, to figure out how many bits of security you would be offering. But this was definitely even just challenging to define this. Level 1 should be enough security for the next few decades, but we went all the way up to level 5, which we think will protect data for a very, very long time. Next slide. It was very cool to see this was a worldwide effort. The submission teams that designed these algorithms were from around the world. They were from academia, they were from industry. Every continent had members represented. There were 25 different countries, 16 different states. And it's been a very international effort. So even though the NIST is a United States agency, it's widely expected that organizations around the world will use these algorithms that get selected. So it was good to see this participation. Next slide. So this shows a little bit more about the 3 rounds of evaluation that we had and the different types of crypto systems that were sent in. The first round lasted about a year, and we had 69 different algorithms that had met all our requirements to be in that first round. And they came from a variety of different mathematical backgrounds. Broadly, there was kind of 3 large families that people tended to use. There was crypto systems based on what are called lattices, also what were called code-based crypto systems based on error-correcting codes, and then multivariate signatures based on multivariate algebra were kind of the 3 big families that we received a lot of submissions from. So in that first round, we held a workshop. We posted these schemes publicly for people to look at, for people to try and attack. We were evaluating them internally as well. In that first round, 25 of the 69 schemes were broken or had significant attacks. Cryptographers like to try and break things, and they were somewhat successful there. At the end of the first round, we selected 26 to move on into the second round. These were the more promising of the algorithms there. They again represented the different mathematical diversity with lattices and codes and multivariate. And that round lasted about a year and a half. Again, some of those schemes were broken and attacked, at which point we selected a smaller number to move on to the third round. We had 7 finalist algorithms, 8 alternate algorithms. And let's advance to the next slide. So that third round just ended, and here's what happened as a result of that. So we selected 4 algorithms that we are going to standardize. For encryption, we selected Kyber. It's the lattice-based crypto system as the main algorithm for people to standardize. We also selected 4 other encryption algorithms to continue to be studied in a 4th round of evaluation. We intend to pick 1 or 2 more of these encryption algorithms. They are not based on lattices, so that we will have a couple crypto systems based on different mathematical techniques. For signatures, we selected dilithium as the main algorithm for people to use. It's based on lattices. We also selected Falcon. It is a lattice-based algorithm that's a little bit smaller, but harder to implement. And we selected Sphinx Plus. It's what's called the hash-based signature algorithm to provide a little bit of diversity there. It's bigger and slower, so it probably won't be used quite as much. But these are the names of the algorithms that people will begin using. Okay, next slide. So even though we've reached this big milestone, there is still work to be done. There's a 4th round that will be for these 4 algorithms, continued study. And we will write the standards. Now that we've named what algorithms are selected, it'll take us a year to write these and publish these. And it's around 2024 that we expect to have the first post-quantum cryptography standards published for people to begin using. We recommend that you wait until that's published to actually put this into your products. Okay, I think I'm getting close on end of time, so I don't want to necessarily go into, I think there's just a couple more slides, but we are going to ask for a few more digital signatures, start a new smaller kind of competition for that to get a couple more signatures. So that's what this slide is talking about, but we can skip it and go to the next slide. The National Cybersecurity of Excellence is running a project to help people know what to do to get ready for post-quantum cryptography. If you're in an organization or an agency and you're wondering about what steps you should be taking. And if we go to the next slide, I've listed kind of some of these steps here. Mostly it involves just finding out what this quantum threat is and starting to make a plan to transition to the new cryptographic algorithms. Make sure your IT staff is aware, your vendors are aware, and that you have a plan in place to transition. So we'll go to the final slide there. So post-quantum cryptography, it's a very fascinating area. It's very exciting seeing how quantum computers affect cryptography. We're very grateful for everything that everyone is doing to help us with this project. And if you want more information, we've got a website, of course, and we have an online mailing list where you can sign up to hear announcements and discuss the algorithms and so on, or you can always contact us directly. With that, I'd be happy to answer any questions that you have, and thank you for, again, the opportunity to speak.
Wonderful. Thank you very much, Dustin. This was a really clear presentation giving us full insight into post-quantum cryptography and the important role of NIST herein. And there are already several questions on the Discord. One is from also Dustin and also from the US. And he has read this week about the recent breaking of SIKE. Let me go to that slide. Here we go, one in the fourth round. He asks, has the recent breaking of SIKE caused any revision to the process or standardization of the other fourth round algorithms? Could you first elaborate on what happened this week and then what will the approach be?
Yeah, so that was big news in this area that over the weekend, Psych, which was one of the algorithms selected for the fourth round, was broken. Some researchers came up with an attack that breaks it in a very short amount of time, very short, small resources, and doesn't even require a quantum computer. It's a completely classical attack using today's hardware. So that kind of thing it's very interesting. Throughout the process, we expect these algorithms to get attacked and broken. That's part of what goes on in this kind of thing. We don't establish trust in a crypto system unless it's been around for a long time and people have tried to break it and had no success. So Psych is broken. The submitters might be able to work out some kind of change to counter the threat. They're still working on that. Psych is one of the newer designs that has only been around for less than a decade or so. And that's one reason why we hadn't selected it yet, because we wanted further study into Psych before we could have confidence. Still, this was a very interesting paper. It has not caused a change in our process because we expect that as time goes, some of these algorithms will be broken. So we'll see what the submitters say in terms of if there's an easy way to thwart the attack. But the likely result is because of this attack, we of course would not be able to standardize Psych if we don't have confidence in it. And an unexpected attack like this certainly gives you, a lack of confidence in the design. So the process is built to handle this kind of thing, and no, we don't have to make any changes as a result of this.
Yeah, and teams involved in the development of Psych, they actually put a 50K bounty, I read, for people who would crack it, and that challenged them.
Yeah.
And actually helped you, right, with assessing the algorithms in the fourth round. So that is great.
So they
worldwide effort.
Yeah, they wanted to get more attention on Psych. So some of the designers are from Microsoft, and they got Microsoft to put up some money to encourage analysis. And I don't know if this is what they were hoping for or not, but yeah, there was $50,000 for this.
Wonderful. Sharma asks, what kind of organizations should be worried about quantum cryptography immediately?
Well, everybody ultimately needs to be aware of this. If you use cryptography to protect your information, which everybody does, even if you are aware of it or not, this threat will apply to you. It depends on what kind of organization you are. If you're smaller, maybe you buy products that handle the cryptography for you. And so you just need to make sure that your vendors and your products will have quantum resistant solutions available. So it depends on who you are, but ultimately everybody will have to transition to these new quantum resistant algorithms, and your level of closeness to the cryptography will correspond to how much effort and work that will involve.
Thank you. Then also from Sharma, could you elaborate a little about what is a lattice-based algorithm versus a code-based, for example?
Sure. The crypto systems we use today, if you look at how they're designed, ultimately there's different mathematical techniques and kind of ideas underneath the surface that they are built using. And it turns out for post-quantum cryptography, that a large number of them are based on what are called lattices. So when you hear the word lattice, you think of kind of this geometric structure that is patterned and repeating. And that's kind of geometrically what a lattice is. What you do is you take a number of vectors in very high dimension, typically like 1,000. So it's a vector with 1,000 entries. And you will take integer linear combinations of these vectors. And geometrically, that creates this repeating pattern, and that's why it was given the name lattice. In 2 dimensions and in 3 dimensions, you can draw it, you can picture it, but when you're up in dimension 1,000, it's hard to kind of visualize. But it turns out using lattices is very, very efficient to do things like encrypt and decrypt, and it gives you a good crypto system. Lattices are probably the hottest area in cryptography for post-quantum cryptography, as well as other cryptographic ideas like fully homomorphic encryption. So lattices are built using this mathematical framework, and there's a lot of results that people have studied and tools that are built to do this. Error correcting codes are another one. They've been used in information technology actually for decades. And they're built on the idea that when you send information over a noisy channel, often some of the bits get changed unintentionally. And if you use an error correcting code, you can actually correct those little errors that occur in transmission using some linear algebra. So it's an older idea, but there have been more modern crypto systems built using that kind of idea and those kind of tools to create crypto systems, and they end up getting called code-based cryptography. Both lattices and code-based end up when you implement them using vectors and matrices and linear algebra to implement them underneath the hood.
Very clear, thank you. Demi from Austin, US asks, organizations might not report breaches or are slow due to various reasons. How will you encourage sharing of information?
Well, post-quantum cryptography, I think, states out now, like we saw with the question on psych, if an academic comes up with an attack or a break, it's a pretty exciting thing, so it gets pretty widely publicized. If someone comes up with a secret attack or an exploit, I'm sure they could keep that secret. So various adversaries might be wanting to do that, like foreign governments and so forth. But in general, most public organizations and industry want to share information about any vulnerabilities or attacks that are discovered. And so it just kind of, that's the way it happens in cryptography. Most of the attacks too, in terms of after you've selected the crypto systems, the vulnerabilities are implementation bugs rather than breaking the actual crypto system. And so there's kind of different categories you could look at as well there.
Great. Taha from Algeria asks, will quantum internet protocols be self-immune, or will they need additional PQC algorithms to be implemented on Alice and Bob's sides?
Yeah, so again, quantum cryptography, and when you say quantum internet, it's usually referring to quantum cryptography. It's related but different than post-quantum cryptography. Quantum cryptography is also known as QKD, quantum key distribution. It can do encryption but not authentication, post-quantum cryptography can do authentication. So you may have to use both if you're interested in using QKD. And so you would combine both of them, but they are different. So an attack on post-quantum does not translate to an attack on quantum cryptography and vice versa. So you have to look at each one kind of separately.
Fantastic. Then a last question, or a few last questions. Suhair from Bangladesh asks, you mentioned how Psych was not even a decade old and NIST did not trust it completely. How old were the other round 3 selections, such as Kyber?
Good question. So the oldest of them is actually Classic McLeese. It's been around for about 40 years. So we're pretty confident security, it has not been attacked. The reason it hasn't been selected is its key sizes are massive compared to the other algorithms. So we're still interested in it. Kyber, Dilithium, Falcon are all based on lattices. Lattices have been used in cryptography probably more around 20 years or so. And even before cryptography, lattices were being studied. So you can go back a few more decades in terms of the theory of lattices that we rely on for security. They are still newer than we would potentially like. And we can't guarantee anything. That's the case with the current crypto systems we use today as well. We can't guarantee that no one will ever attack them. But lattices have been around for a few decades. Sphinx Plus is based on hash-based crypto systems. Those ideas were first developed in the 70s and early 80s. So again, we have a pretty good idea of its security and we're confident in its security, but it's a little bit bigger and slower. Error correcting codes are for Bike and HQC. Like I mentioned, the idea behind them has been around since the 60s, although using them for cryptography is a little bit newer. Classic McLeese is a code-based crypto system, but Bike and HQC, they insert some structure to try and make the codes a little bit more efficient, and that's probably 15, 20 years old for kind of that idea.
Very interesting. Thank you very much. Then last question to straighten it out. David asks to clarify, is PQC indeed only for bits and not for qubit information?
Yeah, so post-quantum crypto algorithms are entirely classical. They run on classical machines. They will use bits. Quantum cryptography, QKD, they will use qubits, photons. They use quantum technologies. So two different worlds that they live in. Yeah. Well, one world, but yeah.
And one world that is united at NIST. Post-quantum cryptography, yes. Quantum, also the development of fundamental techniques towards quantum computing. We already talked about Bill Phillips here, laser cooling and trapping, many groups at both campuses in AMO. So this is wonderful with a broad focus on quantum information, quantum computing. So Suhair says, NIST has to keep a fine balance between how long an implementation has been available and newer implementation that use newer concepts. Thank you very much. And others also very enthusiastic. Thank you. With that, we will conclude this part of today's session. Thank you very much, Dustin, for enlightening us about this topic. It was great having you. And we look forward to having you again another time to elaborate on all the implementations of these algorithms and how to make us quantum resistant using post-quantum cryptography. Thank you again, Dustin, and we look forward to staying in touch.
Thank you.
And the next part will be closely related because we will discuss Shor's algorithm. Jibran Rashid is here to go in depth about Shor's algorithm, and there might be a tutorial as well, right, Jibran?
Right. Hello, everyone. Yeah, today we've got a tutorial as well.
Yeah, so now we will see what will be the key to cracking everything. The last session with Jibran. Can you imagine it? The 10th. Jibran? Yes. Oh, you're happy. It's been an intense time. Yeah, it's great. So the last lecture.
Hopefully
and then
everyone had a good time.
Yeah, right. And this weekend, the last homeworks. And then you will be able to get the Q Silver diploma. Can you mention the change in the submitted quizzes that has been solved now, Jibran? It all took a bit long and now has been fixed.
I'm hoping it's fixed. So yeah, so what QWorld IT kind of looked into and hopefully updated is that if you had previous submissions to the grading server, hopefully your submissions should have been processed now without the error of notebook format not satisfied error. And in case you're going to do a new submission now, please just download a new copy of the notebook file from the assignment, and you shouldn't run into problems, hopefully. Sorry, microphone issues today again.
Yeah, good you noticed. And for QBronze, everyone who fulfilled the requirements, 50% per quiz, 70% in total, until the deadline has received the certificate from QWorld. It was sent to the email address you indicated on Canvas. So if you haven't received it, check which email address you indicated on Canvas and check that inbox and also that spam box. If you really haven't received it and you think you should, send an email to quantum@womanium.org and we will check the list for you.
And also, I think in some cases, people have reported that they have concerns about the name not showing up correctly. So in that case, just send us a mail saying what should be the correct format of the name that should show up. And what we'll do is, rather than sending these one by one, we'll collect them as a batch. And once we've kind of got a reasonable number of requests, then process them as a batch and send out the certificates again with the updated names.
Also, if that is the case, change it right away in Canvas. Otherwise, we will have the same problem for QSilver, the same problem for your quantum hardware certificate, the same problem for the final certificate. So change it right away and please make our lives easier by giving the right information. Thank you very much. Then, Jibran, someone asked about yesterday's slides. Have they been uploaded yet?
Sorry, what has been uploaded?
Have your slides from yesterday been uploaded?
Yeah, the slides were already uploaded yesterday, and I also uploaded a slightly modified version of the slides, which includes the proof of the bound that we just mentioned. So there are two versions of slides uploaded on Canvas, which you can go through, and hopefully they're good. I think there have a couple of typos that were identified, and people mentioned them on Discord. I probably wouldn't get a chance to update the slides for those typos, so it's just a -1, right? So hopefully it's a good exercise for you to figure out where the -1 is off. If you can't figure it out, the Discord chat has a record of where the -1 error is and writing things.
So they are in the QSilver folder on Canvas. Great, right. Take it away, Jibran. Shor's algorithm.
So today, hopefully, I'll be much more brief compared to yesterday. Not to say that the content isn't just as interesting or we don't have enough quantity, but as we mentioned at the beginning yesterday, there's kind of this quantum part of the analysis and the classical part. So because this is a kind of a quantum focused workshop, what I'll do again today is focus on the quantum part of what's remaining regarding order finding. Mention to you the kind of classical connection in terms of reduction of integer factorization to order finding. The details that I will miss out on will be mentioned and are discussed in the notebook files. And if you want more exhaustive, complete details, you are more than welcome to refer back to the references that I shared earlier, right? And if you've still got questions, just message on Discord. Even though the lecture sessions are over, I'll still be checking Discord. So if I see a query, I'll try to answer them to the best of my ability. And hopefully that should take care of it. And you'll be done with me today, so no more boring lectures from my side. So let's start from where we left off yesterday. We kind of introduced the notion of what is an order. We identified the order finding problem. And then today my task will be to convince you that the phase estimation algorithm that we saw yesterday can be used to solve the order finding problem. So that's task one. Task 2 will be then to show why order finding implies, if you can do, if you have an efficient algorithm for order finding, which is exactly what Shor's algorithm is, that is enough to do integer factorization. And that then allows you to break encryption like RSA. Rather than going over some of the technical details, which are covered in the notebooks, what I'll do is also give you a brief kind of connection to how this connects to complexity theory in computer science in terms to in relation to the P versus NP problem that you might have heard of. And it can get a bit kind of unclear if you're not a computer science in terms of what's the relationship of Shor's factorization algorithm in relation to P versus NP. So I'll try to give a quick summary of that as well. Okay, so the order was defined as this integer R, given that we have as input an integer A, and we are working mod N. Integer R is, well, I should highlight. Integer R is the integer in Zn stars that satisfies this property, right? So AR equals 1 mod N. We noted how classically, we don't necessarily know whether or not there is an efficient algorithm for finding this order. If indeed there were, we would already know how to factorize efficiently classically as well. So how do we do order finding using phase estimation? Recall in phase estimation problem, there were two inputs. You had the unitary U and you had the corresponding eigenstate. And so what we'll need to do first of all is to figure out, if you're going to be solving order finding using phase estimation, what's the corresponding unitary we'll be using, and what's the corresponding, well, what are the corresponding eigenstates of that unitary, right? So let's say we've got that capital N, we're working in Zn, and so small n is defined to be log n, standard stuff. Now we define the unitary M sub A, which is just going to take as input, or when you apply to a basis vector ket x, it will transform it to A times x mod n, hence the subscript M sub A. Right, so you've got M sub A, which will take as input a basis ket x and transform it to AX mod n. This is going to be unitary. You can verify it because A inverse exists, hence MA inverse exists, and MA inverse times MA will be equal to identity. Right, so there's a little small exercise over here to convince yourself that this indeed is a unitary transformation. So M sub A will be the unitary that we will use in the phase estimation algorithm. So now recall that in the phase estimation algorithm, if the unitary U is given, it's not U that we actually apply, right? We apply controlled U. So we will have to build a circuit, and this again, I won't discuss in detail. We will have to construct this circuit lambda sub M that will apply M sub A k times to the state X. So what would be the corresponding output state of this transformation? Recall that the first set of M qubits will remain as is, so they'll stay in the state K. And then because I'm just going to be applying this transformation K times, hence the other state will become, the microphone, AKX mod N. Right, so this is the transformation that will get implemented by the controlled unitary circuit. The fact that this can be efficiently implemented can be verified by doing modular exponentiation. I won't discuss it. The second task is to figure out, lambda sub M is just our notation from yesterday regarding what's the circuit that implements the controlled unitary transformation in phase estimation. This was lambda sub M from yesterday, right? And then this lambda sub M was part of the phase estimation circuit that we built. So we are going to be essentially using exactly this circuit. U is now going to be M sub A. And now the issue is to figure out what are the eigenstates of M sub A. And let's assume a birdie came and told us, well, that psi naught, let's say, is an eigenstate of M sub A. And so I naught looks like this. Let's quickly verify that psi naught indeed is an eigenstate of M sub A. So if you apply M sub A to psi naught, you'll just get kind of a multiplicative factor of A in each of these ket states. Let's write it out. 1 over square root R. This becomes, so state 1 will transform to what state? If I apply M sub A to it, recall that this is the definition of M sub A. what should I write over here? Cool, yeah, simple, just A plus, same idea carries along, A times A square, naturally all of this is happening mod n, A cubed, so on and so forth, up till AR, right? Now, how can I rewrite this slightly to make it obvious that this indeed is an eigenstate of M sub A? Right, so this entire thing we want to claim should be equal to some multiplicative factor of psi naught indeed. And yeah, the observation is exactly that AR equals 1 mod n. So we use that property to get the fact that this indeed can be rewritten then as 1, where this 1 is actually kind of this thing, right? AR equals 1, so you've got 1 plus A cubed, and so on and so forth, up till AR minus 1. And that is just psi naught back again, right? So psi naught is an eigenstate of M sub A with eigenvalue 1. Naturally, we want to build a complete set of eigenstates. Let's verify another eigenstate, psi 1. That will look like 1 plus omega arm A plus omega R A plus omega R minus R minus 1 A R minus 1. Right. Recall omega R is just E 2 pi I over R. Verification that psi 1 indeed is an eigenstate. MA applied to psi 1 over square root R. Similar idea. Get A plus omega R minus 1 A square and up till omega R. Did I miss something? Omega R minus 1 AR. Right. Now, how do I transform this in a way such that it becomes obvious that this again is an eigenstate? Do I by omega almost, right? So you can take out omega sub R and you get omega R minus 1 A plus omega R minus 2 A2 plus omega R minus R AR. Right. So this is exactly omega R psi 1. Right. And so in general, you can actually verify that you can build this set of eigenstates, which will have the form 1 over square root R 1 plus omega R minus J A plus omega R minus 2J A square plus omega R minus J R minus 1 AR minus 1. Right, is a construction of the set of states coming from intuition. For the moment, assume we are just given this to us. We are given this. Isn't one missing? No. You've got one, right? I assume you were talking about here. Right. So there's a mathematical verification part of here. Where did these eigenstates come from? So we have at least kind of verified where the construction is coming from for these eigenstates. Going back to the application of the phase estimation algorithm itself, though, there is still now a bigger problem that we face now, right? So what is that problem? If you recall the phase estimation algorithm, it took as input the unitary U, a corresponding eigenstate of that unitary U, and then the output was supposed to be an approximation to the eigenvalue of the phase of that eigenstate. Now, if we are saying that, hey, let's apply that for this M sub A, what's the challenge that we're going to run into right now? What haven't we? We verified the set of eigenstates exists. We know their structure. But if we wanted to now apply this unitary transformation, what would happen? Or what's the kind of key ingredient that we're missing? Think more kind of in terms of actual physical resources that you have. The statement of the phase estimation algorithm was, give me a unitary U, give me a corresponding eigenstate, literally physically, right? So I have to physically build this circuit in which M sub A will be applied via this controlled unitary construction. And I will then apply this Hadamard's in the beginning, apply this QFT dagger at the end. But all of this will only work if over here, I can actually build an eigenstate of M sub A and give it as input over here, right? However, if you note each of the definitions of these sub J's, it assumes kind of we know R, whereas the problem that we are trying to solve is the problem of order finding, i.e. finding R. So we seem to be kind of running into a dead end. I don't know R, so I can't really construct these. We need, so what gives? And here's kind of another nice observation that perhaps a birdie told Peter Shor. It wouldn't have been obvious to me at all. So you make this observation that 1 over square root R so take the uniform superposition of all the eigenstates, right? And you can verify that would look something like this. So let's keep L and some algebra that I will leave you to figure out. That algebra will require you to apply the identity sigma k equals 0 to R minus 1, B minus 2 pi R LQR equals R delta. So you should verify this identity itself to begin with. Assume you have that identity, then you can apply this in the simplification of the algebra for this uniform superposition of all the psi sub k's to finally get, surprise, surprise, just state 1. A naught. So we can have the suggestion that over here, this question mark can be just the state 1 as input. Although 1 itself is not just a single eigenstate, what this has shown is that the state 1 is the uniform superposition of all the eigenstates of M sub A. And because, again, you can verify that the psi sub j's are orthogonal, what you can understand this circuit to be implementing is kind of, or what the circuit will give you as output is kind of a uniform with uniform probability, an output k, such assuming that you had fed in over here one of the psi sub k's chosen uniformly randomly from all the R possibilities. I.e., in other words, just before measurement, assuming you kind of feed in the state 1 over here, the state, the quantum state would have this form: 1 over square root r, sigma k equals 0, r minus 1, phi sub k, psi sub k. So you can have this interpretation that what we're doing, or what the circuit will give us, is an output k, but chosen uniformly randomly with probability 1 over r from one of the possible eigenstates. Right? So what we would have want? So what we get as output is j over 2m, but that j over 2m is an approximation of k over r. Right? So k is the output that we get, and the 1 over r comes in because what we gave as input over here, the state 1, is not just one eigenstate, but rather a uniform superposition of these set of orthogonal eigenstates. Right? So that's one kind of nice key observation that is necessary to kind of make this all work out. Because if the task was to construct this psi sub j for a fixed j or fixed k, sorry, I changed my index variable in between, that won't work. But if you say, yeah, that's fine. But if you say that, hey, I gave this uniform superposition of all the eigenstates as input, and so what the output over here is k, but the output k is obtained by kind of this uniform random distribution over the k different eigenstates, over the r different eigenstates. All right. Now there's another part of the construction that I'm kind of not going to discuss in detail, which is the construction of k over r from the actual output that you get from the circuit, as we discussed last time. That will require application of continued fractions. You can go over the details of that. The other construction that I will post the notes for, because my discussion will be slightly different than the notebooks, is the bound on m. So in this case, what we can show is that m is going to be in O of n, i.e. The number of qubits I need over here are just going to be linear in n, so our circuit is not going to be too bad in terms of its complexity. Right? So the analysis for that I'll post. I won't kind of do it in detail here right now. So couple of technical calculations, those calculations. What we know now is that the order finding algorithm will allow me to figure out this R to a degree of good enough approximation and with a good enough precision, with high probability. So the probability bound is coming just from the phase estimation analysis. The good enough approximation will come from the requirement that M has to be this size, which I'll kind of post in my notes. Finally, what we want to then connect this to is the classical part in terms of why is integer factorization reducible to order finding. Again, there are lots of kind of simplifications that we can do over here. We can just say, hey, your factorization algorithm can just give me one factor, and that procedure I can apply recursively to build this list of entire factors of a given integer n, right? And there's certain other simplifications that we can make regarding the structure of the factors of n, because for some specific kind of structure of factors, for example, if it is a prime power, we already know an efficient classical algorithm to do factorization, right? So we assume for the cases when we know how to do the factorization classically efficiently, we do that. We also assume that already it's enough to just get one factor out because we will be able to apply it recursively and so on and so forth. Then the key idea on which the reduction from factoring to reduction from factoring to order finding depends is the simple lemma that says if you've got an integer n and an x mod n, then x is a non-trivial square root of 1 mod n, i.e. x squared equals 1 mod n, and neither x is equal to 1 mod n nor x equals minus 1 mod n. if this property is true for X, then we can efficiently compute a non-trivial factor of N. This just comes from the fact that if X squared equals 1 mod N, then you can write it as X squared minus 1, which decomposes as this. Given this decomposition, you can apply standard Euclid algorithm classically to construct GCD of X minus 1 and GCD of X plus 1 N. One of them is guaranteed to have the factors of N. And so using Euclid's algorithm to find these common factors will allow you to get one of the factors of N. Then you can apply this procedure recursively to get your entire list of factors. N is being the input and A is being used as a unitary operator. Therefore, we can find our Sherma. Let me make sure I understand the question. Depends on which problem you're asking about. So in the integer factorization problem, the input is indeed N, and I want a bunch of factors. In order finding, the argument was slightly different. In order finding, the problem definition was I've got an integer N, and I've got also an element A in Z n star, and then order R is the integer R that satisfies this property. The order finding algorithm will take as input these two integers. What we will do is an integer factorization, you get as input the integer N, and that then will be transformed to getting in Shor's algorithm. So you can think of this now as Shor's algorithm. Mod some of the classical details that I've glossed over. Here's the key quantum part. Right, so I have access to this integer A, which I've randomly chosen from the set. If it didn't satisfy certain earlier classical checks, then I go in and apply the order finding algorithm, give it as input A, give it as input N, and figure out the order R. Once I have access to R, then I can do this computation. This computation would not have been possible without knowing R initially. Once I know R, then I can compute this. The fact that the reason why we are computing this goes back to the simple lemma that we just discussed previously. Certain other number theory results standing, it is sufficient now to repeat this process to now guarantee that using this computation, we will be able to find a factor D using this GCD of X and N, where the GCD is again computed using Euclid's algorithm. Right? So there are lots of technical mathy details from the classical side that I've glossed over, but hopefully in terms of the big picture, I've convinced you that integer factorization can be solved if I can find this order R. I can find this order R if I can kind of modify the phase estimation algorithm to do order finding for me by constructing this M sub A, which is relatively straightforward via using modular exponentiation. I can apply control M sub A, and then instead of constructing the eigenstates of M sub A, I make this observation that it is enough to consider the uniform superposition of eigenstates of M sub A, which is just the state one. So there are lots of little small kind of exercise over here of verification that this and this and this is indeed true. Finally, what all this shows is that Shor's algorithm can solve factorization in polynomial time on a quantum computer with bounded error. So there are lots of these kind of qualifiers, right? So Shor's algorithm is an algorithm that you will run by default on a quantum computer, not on a classical computer. On a classical computer, you run its simulation. This will not be a zero error algorithm, but you can show that it will have bounded error. So these two requirements, that you're running it on a quantum computer, it's solving it in polynomial time on a quantum computer, but with bounded error, these three properties identify for us within complexity theory the class BQP. And whenever you hear these labels, if you're not very familiar with them, think about them as just a collection of problems that can get solved using an algorithm that runs in corresponding runtime or with a corresponding set of requirements. For the class BQP, the requirement B is bounded error, Q that you're running it on a quantum computer, and P that it runs in polynomial time. So Shor's algorithm is the proof. So it's an exact solution in the sense that with high probability, you'll get the right solution, but the algorithm may be incorrect with some probability, but that probability of being incorrect can be reduced to as small an epsilon as you like, right? And the level of approximation, as we discussed in phase estimation, is an issue if you're doing kind of arbitrary phase estimation. But if you're doing integer factorization, then actually the answer will be exactly correct. But the chances of a single iteration of the algorithm to not work exists, which you can kind of negate by just repeating the algorithm multiple times, right? So that's the bounded error quantum polynomial runtime class. How does this relate to the classical situation for the factoring problem? We know classically in terms of the key kind of poster child problem in complexity theorem problem is that there's a class P, there's a class NP. Let me not draw the Venn diagram because it will be annoying. And then there's also the class BPP, and there's the class BQP. Very quickly, P is the class of algorithms that solve problem with zero error in polynomial time on a classical computer, right? So the defining characteristic is classical, zero error, polytime. So NP here does not stand for not polynomial, it stands for non-deterministic polynomial. And one nice intuition regarding non-determinism in terms of connection to computation is these are the problems for which there is polynomial verification of solution. Right, so not necessarily polynomial generation of solution, which is exactly the open problem in terms of P versus NP, but polynomial verification. And we can indeed verify very quickly that factoring satisfies this property. If someone gives you a list of candidate factors of a given integer n, you just need to multiply out those candidate factors to verify whether indeed or not that list of candidate factors are indeed the factors of the given integer n. So any problem for which any problem that has a structure that given a candidate solution, you can verify in polynomial time that whether or not the given solution is a correct solution, that corresponding problem is said to be in the class NP. So you've got polynomial time verification over here on a classical machine again, right? So that's the class NP. BPP is again bounded error polynomial system. So let me write it out. Bounded error, polytime. That's the first P. And classical. Right, so BPP is kind of the classical analog of BQP, not NP, because NP is non-determinism, whereas BPP is randomization. And so usually when we are talking about classical classical algorithms, you've got kind of these three kind of key structures. Either you've got a deterministic algorithm, which always works. You've got a non-deterministic algorithm for which you've got the structure of verification rather than generation. And then you've got randomized algorithms, which correspond to the bounded error kind of classes. So if you've got a randomized algorithm, which works in polytime on a classical computer, then you've got a problem that can be solved in the class BPP. And BQP then is the quantum analog of it, bounded error, polytime, but on a quantum computer, not on classical, right? So BQP is really the quantum analog of BPP. Now, what we know about factorization, well, first, we know that P is in NP, but we have no idea in terms of the relationship of whether NP is in P or not. That is indeed the P versus NP problem. Thank you for sharing the complexity class. That's right. Is that so? It has, okay, that's fine. Now, factorization is known to be in the class NP, but within NP, there's an additional class of problems called NPC, or what you call NP complete. Now, NP complete problems are interesting because when people try to solve the P versus NP problem, they ran into they try different attempts. And one attempt is to say, hey, can we identify the hardest problems in the class NP? They're hardest in the sense that if I can solve one of these problems, then I can solve every other problem in the class NP in polynomial time as well. So, for example, given a Boolean formula, is that Boolean formula satisfiable or not? This problem is kind of the candidate, kind of the poster child example of the class NP complete. However, factorization and graph isomorphism are two kind of interesting problems that are known to be in NP, but are not known to be NP complete. And so here's the emphasis, right? It's not that I'm saying they're definitely not NP complete. It's just that we don't know. So we don't know whether they're NP complete or not. So they are in NP. We don't know whether they're NP complete or not. And so that's why, even though Shor's algorithm is a really big deal, it didn't become even a bigger deal because we don't know whether or not factorization is indeed in the class NPC or not. So why am I kind of giving all this background in complexity theory in crash course? Because you'll hear one of the key kind of misgivings thrown around that quantum computing gives you an exponential advantage over classical computing via Shor's algorithm. And there's a part of it that's actually not proven, because even though currently we don't know of an efficient algorithm for factorization on a classical computer, it also hasn't been proven that factorization cannot be done efficiently on a classical computer. It's strongly believed that we may not be able to do so, but we don't have a proof. And so that's the kind of the one assumption in here that sometimes kind of in popular discussions gets lost. So it's very much possible that tomorrow some smart students like you figure out an efficient classical factorization algorithm. And that's kind of going to be much more interesting in some sense regarding, hey, how do we treat now the distinction between classical computation versus quantum computation? So this also meant that just because factorization is in BQP, it automatically didn't imply that P equals NP, because factorization is not something that is NP complete. So that means that it's not necessary that BQP solves NP complete problems in polynomial time. So for the other direction would be, if tomorrow someone shows that factorization is indeed NP complete, then Shor's algorithm would be solving an NP complete problem in polynomial time, which again is something people in classical computer science really believe is probably not the case, right? So if you've been to Scott Aronson's blog, there are a lot of blog entries that can really emphasize this fact. So it's strongly believed that while quantum computation does give you advantages in kind of lots of classes of problems, but it's not powerful enough such that it will solve NP complete problems in polynomial time. And so we are left with this much more nuanced understanding and incomplete understanding of how these different classes of problems relate with each other. All right. So with that, I'll finish my discussion today and give Sabah hopefully enough time to give you a tutorial on phase estimation and order finding kind of done on Qiskit. Thank you very much, everyone, for giving me the opportunity to speak to you for so many sessions. It was wonderful, and hopefully you had fun. Sabah, it's all yours. Sorry for going over time. I know you should have had more time. Thank you. I know this was kind of rushed, so if you've got questions, feel free to post on Discord, and I'll kind of respond to queries there.
Will you still stick around during Sabah's part, Jibran, or time for you to leave?
Yeah, I should be here. I should
still be there?
No,
okay, great. Yeah. Then, while Sabah is preparing, and during the part, everyone, please, if you have general questions to Jibran, if you want to say thank you notes, write it down, and at the end of the session, we'd like to have a brief few minutes, Jibran, before you leave.
Sure.
Wonderful. Then one other general announcement. Tomorrow is the deadline to sign up your team and challenge for the hackathon. We already got great team and team names and challenges. Even today during the lecture, there have been many signups. I will tell you some names. We have B random with a B. We have random qubits. We have 5 qubits, quantum vol, cryptq, quartermaster, entangled web, team Nepal, also great, quantum artist, business as usual. So the name competition is already going on. Quantumania. I am very glad to see, oh, Schrödinger's ensemble, great. I am very glad to see there is a really good distribution of challenge picks. First choice, second choice, that is great to see. Encourage everyone to sign up today, latest tomorrow, and then this weekend we will confirm your preference for the challenge and team, and look forward to a really exciting time. The next 2 weeks, the mentors are coming in from the companies, and it will be very exciting with the teams, with the mentors, and then competing for the best solutions, but especially get insight in the problems and learn. I will have a look if Saba is there as well. Yes, and you are co-host, Saba. Then I won't take more of your time as well. And we will see you for a few minutes at the end, Jibran. Thank you.
Okay, so hi everybody. You can hear me, right?
Yes, we can hear you, Saba.
Okay, so let's begin. Sorry. Yes.
Is there anything that everyone already can prepare or get, Saba, or will you start showing first?
Sorry, I couldn't hear your...
Okay.
Okay.
This looks good. Please just take away the Zoom controls.
It's, I mean, my screen is flashing right now, and sometimes it crashes. So I will going to give it some, 30 seconds or so. Oh, boy.
We will wait briefly until everything works technically for Saba. Then a question to all of you. Is the team finding going well on Discord, or is there a need for breakout rooms with the opportunity to find a team tomorrow? I would like to see some hands in the Zoom if you would like to have some interaction tomorrow in breakout rooms to still find your team. Let me please keep them up. I will go to the participant view. I don't really see hands, which is what I wanted to see. That is great. I also recognize many names that signed up. So that is great too. So interpreting from this, from your group, there is no need to, oh, I see a hand. Feel free to send me a message as well, the person who is interested. All right. Okay, but there is no big need, and I also recognize many names that are all set. Great. Saba's PC is restarting. Jibran, if you are there, do you want to tell a little bit more about what Saba is going to show and some tips and tricks to finish Q Silver?
So you can hear me, right?
Yes.
So I think the plan was exactly because the last session and today's session were a bit perhaps too abstract, to focus on specific examples of using phase estimation and order finding using the Qiskit notebooks that we have in our tutorials, so that people kind of get an appreciation of, all right, how are all of these things connecting. And then some of the steps that I kind of also glossed over. So for example, that M sub A, the control application of M sub A, seeing that in practice, how to construct it, the notebooks go over that. The continuing fractions, I think, I'm not sure whether Sabha will actually explicitly do the continuing fraction examples, but they are at least there in the tutorial notebooks. So the couple of things that I have glossed over, all of them are covered in the notebooks, and I strongly recommend people to review those. I think the session, the lecture session plus the notebooks will give a complete picture. There are, as I mentioned, there are two calculations that are slightly different in my presentation than the notebook. It's about figuring out the approximation and the precision level in your kind of answer and the probability with which you're calculating it, the bound on that. The presentation, I think, in the lecture, in the notebooks is from Nielsen and Shor. So people are more than welcome to review that as well. I have used John Rochester's lecture notes to give the presentation of the calculation on the bound, and David Merman's lecture notes, the quantum computer science book as well. So you can kind of refer to either one of them or some other resource if you prefer those, and it should be perfectly fine. And I think yesterday there was a question about, do we need to know Shor's algorithm for finishing of silver? And I think that's also partially motivated by the fact that when you look at the assignments list and the quiz list, you've got QPE order finding, and then that's it. And I think part of that has to do with the fact that, as we discussed today, it's when you do QPE and you see the reduction of QPE into of integer factorization to order finding, that's almost already Shor's algorithm of itself, right? Once you've seen that phase estimation algorithm can be used to do order finding, and then that in fact is Shor's algorithm. And that's what kind of the assignments and the quizzes kind of leave it off at. Some of the classical part, if you see in the notebooks, is left as optional. So people who are interested can read it and look it up. But the exercises kind of finish off at QPE and order finding.
Great. Thank you very much. And we have had you, Jibran, from QWorld here for 10 sessions for 2 modules and certificates, Q Bronze, Q Silver. Could you tell more about how to get involved with QWorld more? Q intern possibilities, starting an own QWorld initiative. It would be great if everyone here could help QWorld grow and flourish.
Thank you for the opportunity. So the first thing that I kind of usually hear, and QWorld in general hears when kind of these 2 workshops get over, is when are you coming up with the next workshop? And while indeed we would love to come out with more content, between kind of our regular day jobs and doing these workshops, it leaves little time to kind of create new content, although we are actively working on it. And I noticed that in our forum, there are lots of people with diverse backgrounds and specializations and interests. One of our challenges in the hackathon is as well regarding creation of quantum hardware tutorials. That's based on feedback that we get from lots of computer science students saying, hey, you told us this abstracted version of qubits, but what's really going on under the hood? So if you enjoy these tutorials and you've got a physics background, you're more than welcome to kind of maybe as part of the hackathon, also perhaps independently if you want to do it. You could join QWorld and help us in creating this additional tutorial content. It need not just also be about quantum hardware. It can be about some other specialization. For example, some people may have interest in quantum machine learning, application to natural language processing. When you're talking about recent kind of practical applications of kind of current NIST devices, optimization techniques that have been used recently is something that you've seen we haven't really covered in our tutorial. So tutorials focusing on that would be really useful. So that's one key thing. And then building on top of that, what we have also is a Q intern program that usually runs during the summer months. Some summers are more active than others. And the idea there is you can either take up creation of this academic content as part of the challenge, as well as perhaps take on a research project with your local faculty or with one of the faculty members that are available within the QWorld network. And if you've got something else to propose from yourself as well, that, hey, this would be an interesting initiative that you haven't thought of, that would be great. What we also do is we have a Q cousin initiative where the idea is where countries where people might find it difficult to kind of create this threshold level of quantum community, then you can get started by kind of becoming a member of QWorld on kind of a group level, which is called a Q cousin. There are about 18, 19 countries last time I checked that are Q cousins. And then the idea is that the QWorld community interacts with the Q cousins on kind of a more semi-official level. Q cousins then are expected to also create additional workshops locally, and that helps in kind of perpetuating the information, right? So those are kind of the key few things that I come to mind right now. People
I heard there is already interest from Japan and Norway to start an own Q cousin. Who should take contact to do this?
I think just dropping a mail to QWorld, if you just go to the QWorld website and just drop an email, that's good enough. Yeah, and I think that usually what's required once you kind of drop in that mail and things are organized, what QWorld calls is an entangling event, which essentially ends up being offering of a Q Bronze workshop for this specific Q cousin organized by the QWorld community. And that allows the local kind of Q cousin community to figure out what's expected in organizing such a workshop. And then from there, hopefully things go on.
And for the Q intern projects, how long are they usually? Because this could be a great opportunity after the 2-week hackathon to dive into a longer project.
So the Q intern projects themselves are just for the summer, but then the projects that perhaps show promise and are longer, then kind of continue as independent projects later on as well. So while Q intern itself is smaller, but it has the potential to continue longer, assuming interest by both the advisor and the internees. We've had reasonable success in the sense that a few projects have led to publications, and then QWorld has its own kind of smaller online conference called Quantum Science Days that usually happens at the start of June. And those results and that work has been kind of presented in that conference. Some of these talks should be online as well on the QWorld YouTube channel.
Yeah, I can recommend everyone to watch them back. It was extremely interesting, including sessions on quantum games, showing everything that is available, everything that you can play, the whole quantum game ecosystem, and various Q intern topics. Yesterday we had the Q intern flash talk here, right, about quantum natural language processing. So those are some good examples. Bakao asks, is QGold happening?
As I mentioned, yes, you've got all the elements in the periodic table, so potentially we can go on with them. Yes, we are in the process of creating additional work. There's a Q nickel, for example, that we didn't really touch upon. It's kind of intermediate between Q bronze and Q silver. That content is already there. One thing that I didn't mention, one of the kind of my personal projects within QWorld as well is to build these workshops into a full online degree program for quantum. So imagine, one course in quantum algorithms, one course on quantum foundations, and so on and so forth. That leads to a master's level online degree for quantum computing. Naturally, we're in the initial phases of that. Towards that end, what we have been doing since last fall is offering a combination of Q bronze and Q silver as a university level course in collaboration with the University of Latvia. So the idea is people take this Q course during fall. It will be offered this fall as well. So in case you're someone who was attending these talks but wasn't able to complete the assignments or wouldn't be able to complete them, a good opportunity for you would be to enroll in Q course in the fall. It will be a combination of bronze and silver, then probably a semi-independent study after that to complete the requirement of a full single online graduate degree graduate course. And you'll get a certificate from the University of Latvia Faculty of Computing that can transfer to credit to your local university as well. And that then hopefully over the next few years can transform to a full bunch of courses that constitutes a master's degree online for quantum computing. So USA is perhaps too big to form one Q cousin, but there was some internal discussion where people suggested, yeah, we could have Q Massachusetts, Q Boston, or Q Pennsylvania, stuff like that. It really depends on kind of interest, right? So if there are people within a certain community who are interested in starting an initiative at the, let's say, the state level, then it's more than welcome.
Jibran, we asked many speakers what their advice is for everyone on their quantum journey and entering their quantum careers. What is your advice for everyone?
I'm too much of an academic to give career advice outside of academia, given how practical quantum computing is supposedly becoming. I don't know. It's basically just, have fun. And, you'll figure out what you like and what you enjoy. If I look back when I was starting out, one of the perhaps not good or wise decision to do quantum computing was, hey, this is really, a cool enough field, but still theoretical enough such that it will never become practical. Little did I know, 15 years down the line, everyone is talking about building one practically. So that's really cool. Kind of I should add, the motivation for why I was interested in it not being practical, because then, you've got these still, I think, valid ethical issues to be concerned about. And Ronna DeWolf has a nice kind of paper on it as well, right? In terms of, hey, as scientists, what's the responsibility we have in terms of following these cutting edge sciences, in terms of now making sure that it is equitably kind of uniformly distributed across the world. This workshop is kind of a great initiative towards that end. And so you see what's happening in quantum computing now because of large scale funding that, people and scientists are kind of getting geographically limited, that, hey, I'll be working in this area for this country and so on and so forth. And so that's something 15 years ago, I thought I wouldn't want to run into. And that's why I was like, hey, it will remain theoretical, so I'll just keep doing it. But naturally, if it's practical, there's definitely much more interest. In terms of career advice, just do what you like.
Yeah, and that is a great advice. Just have fun. And clearly you have fun because you are doing this in your spare time. For all of us, it is around, it's 11 p.m., I think, at your place. And you do this for your work. You organize this in your spare time. For all of us, we all learned so much, so enlightened. Many people got their QBronze diplomas, 430 people. Additionally, around 150 people had already gotten one. So around 550 people or even more got that established in this course. Now continuing with QSilver, growing in quantum programming and algorithms. We are extremely grateful to you, Jibran, to take all participants on this journey, and so thoroughly, so insightful, such great interaction with everyone, so smooth. There was no need for me to ask questions, right? You are the perfect multitasker, as if you are in superposition like a qubit with your own notes and mentoring everyone entangled. Our thanks couldn't be bigger. We will see you around on Discord. We will be in touch for more initiatives, and the hackathon problem of challenge of making quantum hardware modules or other interesting QWorld modules that can be taught will be a great challenge to which we invite people to sign up if you are interested.
More than welcome. I think just a quick update. It seems like Saba's PC might have crashed rather than just restarting, because I don't see her online on Discord.
Shall we organize a separate tutorial session this weekend if people have demand, if people need it? And then for now, we will ask everyone to work on it yourselves. It means you have a little bit more time to work on today's quizzes and go through the notebooks. Yining and various of you have done an amazing job in the mentoring sessions every morning. I am sure there will be one tomorrow too, so feel free to join there to help each other and to solve the quizzes and exercises. This is your last chance all to ask live questions to Jibran.
In person, but if there's a need, I'll see if Saba is available for the tutorial, if there's demand as well, and we can have that scheduled. If that's not possible and there's a demand, maybe I can do it as well. Ideally, I would have done it already right now, but I didn't kind of set up my machine for running the session. And by the time I set it up, it might be too late. So if people feel like that they're having issues working through the tutorial notebooks, please let us know. And for sure, we can have the tutorial session later that we missed out on today.
Fantastic. And with that, we conclude today's session. Post-quantum cryptography, Shor's algorithm. Thank you very much, Jibran, for today.
Thank you. Thank you, everyone.
And we wish everyone
good
luck
Malu,
finishing these models. Yeah, it was great collaboration with QWorld, Jibran. Very happy. Yeah, a big applause from everyone to Jibran. And we will see each other very often again. Thank you so much. Everyone sign up for the hackathon today, latest tomorrow, and many more exciting quantum coming up. Thank you.